The graphics card has become the ultimate symbol of technological excess. It is a brick of silicon and copper that dominates the interior of every high-end PC. We are told it is necessary, but we are rarely told why. If the central processor is truly the brain, why does it need a second much larger brain just to show us pictures on a screen? It feels as though we are building a monster with two heads, one that thinks and one that merely observes. This is the central mystery of the modern computer, and it is a question of economics, physics, and the very nature of intelligence itself. Before we dive into the heart of the machine, take a moment to consider the path we are on. We are living through a revolution where the tools we use are becoming more complex than the problems they solve. If you find this exploration of the digital soul intriguing, please consider subscribing to the channel. We are here to pull back the curtain on the things we take for granted. Your support allows us to keep asking the difficult questions about the world behind the screen. Now, let us begin the journey into the Silicon Divide. Imagine, if you will, a grand university hall. At the front of the room stands a single elite professor. This individual is a genius of the highest order, capable of solving complex differential equations, composing a symphony, or debating the nuances of ancient philosophy. This is your central processing unit, the CPU. It is the most sophisticated piece of engineering on the planet, designed to handle any task you throw at it with absolute precision. It is the general, the architect, and the philosopher of your computer. But now, imagine a different task. Imagine you have 1,000 small children in a massive playground, and you give each of them a single simple job. You tell them to write the number 1 on a piece of paper and then add 1 to it. Individually, these children are not geniuses. They cannot solve calculus or write poetry. But there are 1,000 of them, and they are all working at the exact same time. This is your graphics processing unit, or the GPU. The conflict between these two forces is the story of modern computing. We naturally assume that intelligence should always win over quantity. We believe that a smarter brain is always better than 100 dumber ones. However, the digital world does not always reward brilliance. Sometimes the world is so vast and so repetitive that brilliance becomes a bottleneck. In those moments, the genius professor is overwhelmed not by the difficulty of the task, but by the sheer volume of it. Let us conduct a thought experiment to see where the professor fails. Suppose you need to write the phrase 1 + 1 = 2 5 million times. The professor is incredibly fast. He can write the phrase in a fraction of a second with perfect handwriting, but he can only write one phrase at a time. He must finish the first, move his hand, and start the second. Even at his lightning speed, the physical act of moving from one line to the next becomes a limit. Now, look back at the 1,000 children. They are slow, and their handwriting is messy. It takes them 10 times longer than the professor to write that single phrase, but they are all writing at once. While the professor is finishing his 10th line, the children have already finished 1,000. By the time the professor reaches his 1,000th line, the children have finished 100,000. The smart approach, which processes things one by one, collapses under the weight of massive repetition. This is the reality of your computer screen. Every single frame you see is made of millions of tiny dots called pixels. For every one of those pixels, the computer has to calculate a color, a brightness, and a position. If you are playing a game at 60 frames per second, the computer is performing these calculations 60 times every single second. Even the most brilliant professor in the world cannot keep up with that many simple chores. He would spend all his time doing math for pixels and have no energy left to actually run the program. To understand how we reached this point, we have to travel back to the 1980s and early 1990s. In those days, computers were simple. They displayed text or basic two-dimensional shapes. The screen was a grid of simple colors, and the math required to update those colors was minimal. Back then, the CPU was truly the king of everything. It handled the logic of the game, the input from the keyboard, and the image on the screen simultaneously. Dedicated graphics hardware was almost non-existent in the home market. You didn't need a massive add-on board because there wasn't that much to draw. The CPU would simply tell the monitor which dots to turn on, and it was done. It was a world of flat images and limited palettes. But as the 1990s progressed, a revolution was brewing. We stopped wanting to look at flat pictures. We wanted to look into three-dimensional worlds. The jump from 2 dimensions to 3 dimensions wasn't just a visual upgrade. It was a mathematical catastrophe. In a 2-dimensional game, a character is just a flat image moved across a grid. In a three-dimensional game, a character is a collection of thousands of triangles existing in a virtual space. Every time the character moves or the camera turns, the computer has to recalculate the position of every single corner of every single triangle. This is the birth of the polygon. When you add lighting into the mix, the complexity explodes. The computer must calculate how light from a virtual sun bounces off a virtual wall, hits a virtual floor, and finally reaches the virtual eye of the player. It has to account for shadows, reflections, and the way colors bleed into one another. We are no longer just drawing dots. We are simulating the physics of light and geometry in real time. This was the moment the professor realized he could no longer do it alone. By the mid-1990s, companies like NVIDIA and 3DFX realized that if we wanted these 3D worlds to look real, we needed a new kind of worker. We needed the Schoolkids. They created dedicated chips designed to do nothing but the simple, repetitive math of 3D geometry. These were the first true GPUs. They weren't smart in the way a CPU is. You couldn't run a word processor on them or manage an operating system. But they could chew through millions of triangles in the blink of an eye. This specialization changed everything. The CPU was finally free to focus on the soul of the machine, the artificial intelligence of the enemies, the physics of the world, and the complex logic of the software. The GPU became the muscles and the eyes. It took the abstract numbers from the CPU and turned them into the beautiful, fluid images we see. It was a partnership of necessity. The separation was not an act of bloat, but an act of survival for the computer's performance. You might ask, why not just make the CPU stronger? If we can put more transistors on a chip, why not just put 4,000 CPU cores together and call it a day? The answer lies in the fundamental design of how they think. A CPU is a generalist. It is designed to be branchy. It has to handle if-then statements. If the user clicks here, do this. If the file is missing, do that. To do this well, a CPU needs a massive amount of overhead to ensure it never makes a mistake and can switch between wildly different tasks instantly. A GPU, on the other hand, is a specialist in parallelism. It doesn't care about if-then statements as much as it cares about do this to everything. If you want to make the whole screen 10% brighter, you don't need a genius to decide that for each pixel. You just need a worker who can add 10 to every value simultaneously. Trying to make a CPU act like a GPU is like trying to use a scalpel to mow a lawn. It is the wrong tool for the scale of the job. This brings us to the physical reality of these devices. If you look at a modern graphics card, it is enormous because it has to be a self-contained ecosystem. It has its own dedicated memory, known as VRAM, which is much faster than normal system RAM. It needs this because moving data from the main memory to the GPU creates a bottleneck. To keep those 1,000 Schoolkids working, they need the supplies right next to them. They cannot wait for a truck to deliver data from across the motherboard. Then there is the issue of heat. Every time a transistor flips, it releases a tiny burst of thermal energy. When you have billions of transistors flipping billions of times per second, you are essentially running a space heater. Because GPUs have so many more cores than CPUs, they generate an incredible amount of heat. This is why the card is covered in massive metal fins and multiple fans. If you tried to pack all that power into the tiny space of a CPU, the entire chip would melt in seconds. For many people, the idea of a dedicated GPU seems like overkill. This is why we have integrated graphics. These are the few Schoolkids who live in the same house as the professor. They are built into the same chip as the CPU. For writing emails, watching videos, or browsing the web, they are perfect. They are efficient and cheap. But the moment you ask them to build a complex 3D city or render a high-definition movie, they are overwhelmed. The scale of the work simply demands more bodies than can fit on a single small chip. This modularity is actually one of the greatest strengths of the personal computer. It allows us to customize our machines based on our needs. A scientist might need a massive GPU for simulating the weather, while a writer might never need more than a basic integrated chip. This flexibility allowed the PC to dominate the market. It became a platform where the hardware could evolve as fast as our dreams did. We didn't have to wait for a whole new computer. We just had to swap out the laborers. As the years passed, we began to realize that the GPU is talent for dumb math was actually a hidden superpower. In the early 2010s, researchers discovered that the same math used to calculate light and shadows was almost identical to the Math used for complex scientific simulations. Suddenly, GPUs weren't just for games. They were being used to fold proteins for medical research, simulate the birth of galaxies, and crack the most difficult codes in the world. This led to the AI gold rush we see today. Artificial intelligence, specifically deep learning, relies on something called neural networks. These networks are essentially just massive layers of simple arithmetic repeated billions of times. It is the ultimate repetitive chore. To train an AI, you don't need a philosopher who thinks deeply about the meaning of words. You need a billion laborers who can adjust tiny numerical weights across a massive grid. The GPU was the perfect candidate for the job. This is why graphics cards have become strategic global resources. They are the engines of the next industrial revolution. When you see news about countries banning the export of high-end chips, they aren't talking about CPUs. They're talking about GPUs. The ability to process data in parallel has become the new oil. It is the fuel for every large language model and every self-driving car. The massive add-on board that Raimu found so irrational is now the most important piece of silicon on the planet. But even as we reach these heights, the cycle is beginning to turn again. We are starting to see new architectures, like the ones in modern smartphones and high-end laptops, where the CPU and GPU are being merged more tightly than ever. These systems on a chip try to balance the efficiency of integration with the power of specialization. We are moving toward a future where the distinction between the brain and the muscles might blur, but the fundamental need for parallel labor will never go away. The story of the GPU is a lesson in humility for us all. It reminds us that being the smartest isn't always the most important thing. Success often comes from the ability to work together, to handle the small things at a scale that no individual can match. The graphics card is not a flaw in the design of the computer. It is a monument to the power of collective effort. It represents the realization that to see the world in all its complexity, we need more than just a single brilliant mind. When you look at your computer next time, don't just see a collection of expensive parts. See a society of silicon. See the professor and the 1,000 children working in perfect harmony to create the digital world you inhabit. We often value the brain and the idea, but we must never forget the hands that do the work. The cost of a GPU is not just a price tag on a piece of hardware. It is the price of simulating reality itself. In our own lives, we often try to be the CPU. We try to handle every task, solve every problem, and manage every detail by ourselves. But perhaps there is a lesson in the GPU's success. Sometimes we need to delegate. We need to find ways to work in parallel with others. We need to recognize when a task is too big for one genius and requires 1,000 small helping hands. True efficiency isn't just about how smart you are, but how you organize the work that needs to be done. So the next time you feel overwhelmed by the sheer volume of your daily chores, ask yourself if you are trying to be a professor doing the work of 1,000 children. Maybe you don't need a bigger brain. Maybe you just need a better system for handling the repetition. Life, like a computer, is a balance of high-level logic and low-level labor. Finding the harmony between the two is the secret to moving forward without burning out. Thank you for joining us on this deep dive into the heart of the machine. It is a journey that takes us from the simplest dots on a screen to the edge of artificial consciousness. We hope this has given you a new perspective on the brick sitting inside your PC. If you enjoyed this narrative, please subscribe and hit the notification bell. It helps us continue to produce content that explores the intersection of technology and philosophy.